Hello everyone, welcome to our differential equation class. In this video we are going to use the Laplace transform method to solve differential equations with discontinuous sources. First we are going to introduce the type of discontinuous sources we are going to work with, which are constructed with step functions. We are going to compute the Laplace transform of these step functions, and then we are going to use them to write down translation properties that the Laplace transform has, and with these translation properties we are going to be able to solve differential equation with discontinuous sources, as we are going to see it in a few examples. So that's the plan for today. Let's start introducing the type of discontinuous functions we are going to work with, which are step functions. So we denote the step functions by u of t, and this is a function that is 0 for t negative and 1 for t 0 or positive. So this function is discontinuous at t equals 0, as we can see in this picture. 0 for t negative, 1 for t 0 or positive. So this function has a discontinuity at t equals 0. That's why it's called a step function, but they are also called Heaviside functions, in honor to Oliver Heaviside, who made them very popular in the 1880s when he used them to describe switches in electrical circuits. Heaviside is also famous because he rewrote Maxwell's equation for electromagnetism in the way that we use them today. The original way Maxwell wrote the equations is a very complicated way and is not in use today. You go to any electromagnetic book, and the way they are writing the Maxwell equation is Oliver's Heaviside way. So we are going to work with the step function, and also with the step function shifted to the right by a constant c or to the left by a constant c. So these are the graph of these two functions is of the shift of these two functions looks like this. So when we shift the function to the right, essentially what we do is in the argument we subtract c. C is a positive constant. So suppose this is the value of c. So then this is the function that is going to be 0 until we reach the value c, and then it's going to take value 1. So the whole function is shifted to the right by c. For example, to fix idea, suppose c is 3. So this is how the function looks like, the step function with step at 3. So ut minus 3. But we can assume that also c is negative, so then we are going to be shifting to the other side. So when c is negative, for example here, and let's fix idea, c is negative 3. So the step is here. So then u of t minus 3, you see what that is equal to. This is equal to u t plus 3. So this is the shift of the step function to the left by 3, because it's a shift to the right by negative 3. So this is how the function looks like when we shift the step to the right or to the left. This is how they look like analytically. This is the graph, and this region we are shading here is the region where we need to integrate to compute the Laplace transform of these functions. So when we compute the Laplace transform, we are going to need to integrate in this region. So we are going to have the discontinuity in the region we are integrating. But look what happens when we shift the function to the left. We are integrating in this region, so on that region the step function is identical to the function 1. So for the purpose of computing the Laplace transform, the function 1 of a step shifted to the left are the same. So now, let's having these pictures in mind, let's compute the Laplace transform of the step function. And the result, of course, depends on whether we are shifting the step functions to the right or to the left. So if we shift the step function to the right, then this is the result for the Laplace transform, and the Laplace transform converges for the values of s positive. And then if we are shifting the Laplace transform with the step function to the left, its Laplace transform is just 1 over s. So let's see why this is the case. So let's compute solution, or in this case should be proof. How do we prove this result? Well, we need to compute the Laplace transform. It's not we have the step shifted by c, and this is always the limit. By the definition of the Laplace transform, this is the limit when capital N goes to infinity of the integral from 0 to capital N of the exponential negative st. And now we need to put here the step t minus c dt. But let's go with the definition of what is the step, and let's consider the case c. Let's start first with the case c bigger or equal 0. Let's start there. So we are in this situation, and what is going to happen? We are going to integrate the function step from 0 to infinity in this region. Notice that from 0 to c in this interval the function is 0. So we actually can integrate from c to infinity because this part is 0. So we can integrate from c to infinity. And notice that on that interval the function takes value 1. So what we can do here is, this is going to be the Laplace transform of the step t minus c. Recall c now is non-negative, is the limit n goes to infinity, but now we can integrate, because the step is 0 for t less than c, we can integrate from c to n, and in that region we still have the exponential negative st, but the step is going to take value 1 dt. So it's very simple. Now we have two cases. Suppose s is 0. If s is, okay, let's put it with an if s is equal 0, what happens in that case? Well, then the limit, what we have here is the limit n goes to infinity of the integral from c to n of 1 multiplied by 1 dt. So this is going to be just n out the limit n goes to infinity of the function n minus c. Well, but this is infinity. So the Laplace transform diverges for s equals 0. So we can, so diverges. So we consider the case s different from 0. And now you know why we did that, because when we compute the Laplace transform of u t minus c, and recall we are now here, so this is the limit capital N going to infinity of the integral of cn exponential negative st dt. Now we can do the integral because s is different from 0, so the integral here is going to be, if we do it, the integral here is going to be, well, first we compute the limit n goes to infinity, then 1 over minus s. You see, s has to be different from 0, so we can do this calculation. And then here we are going to have the same integral evaluated at negative Sn minus exponential negative Sc. And now we need to take the limit, and this limit, well, it has two results depending on the value on the value of of S. So if S is negative or if S is positive. And what happens when S is negative? If it's negative, negative is positive, this diverges. Then goes to infinity. And if S is positive, then we have this negative sign here that makes the limit to be 0. So what we end up with is that the Laplace transform of u t minus c is equal to this factor. This is 0, so times this factor. So this negative sign and this negative sign, they are going to cancel out. So we are going to have a positive exponential negative cs over s. But this is only for s bigger than 0, and recall we are in the case c non-negative, which is what the theorem says. So now what happens, let's make it a little bit nicer. What happens in the case c negative? So now we need to study the case c negative. Recall this, what we obtain here, this formula right here is that formula here. So now we need to see what happens here. Well, but in the case c negative, recall we are trying to compute the Laplace transform of the step in this case where c is negative, but in that case we are integrating always in between 0 and infinity, and in this case the step function is identical to the function 1, and because of that we know what the Laplace transform is going to be. The Laplace transform of u t minus c, recall c is negative, then this is exactly the same as the Laplace transform of the function 1, no matter how negative c is. And we know what that is. This is the integral from 0 to infinity of exponential negative st dt, and we have computed that in a previous video. We obtained 1 over s for s positive. And this is what we say in the theorem, that the Laplace transform is. So that is how we compute the Laplace transform of a step function. The step function is very useful to write down a couple of translation properties satisfied by the Laplace transform. This is the first translation property that says that whenever you have a function f of t and you shift the function to the right by c and also multiply that function by a step function also shifted to the right, the Laplace transform of all that is related to the Laplace transform of the original function without the shift, and the relation is that you need to multiply this Laplace transform by an exponential that contains the shift c, exponential negative cs. This is for c positive or 0. And then there is a second Laplace property of the Laplace transform, a translation property that is kind of the opposite of the first property, and is this. If you now multiply a function by an exponential and you do the Laplace transform of that multiplication, this is the same as the Laplace transform of the original function without the multiplication, but this is going to be a function of s. Well, shift that function into s minus c. This is what we mean here, and that is the second translation property. So the first property says that if you multiply a Laplace transform by an exponential, this is the Laplace transform of the shifted version of the function. Now if you shift the Laplace transform itself, this is the Laplace transform of the original function multiplied by an exponential. So you can see they are kind of, one is the opposite of the other property. One property is for the shift positive, so positive or 0. The other is for any value of the constant c. Let's see how these properties actually look like in a particular example. suppose, just to fix idea, the function here we are talking about, suppose it's a cosine of 2t. So if this function f is a cosine, well, we know what the Laplace transform of f is going to be. It's going to be the function Laplace transform of the cosine, which is s over s squared plus is cosine of 2t, so 2 squared for s positive. Okay. So for that function, how does it look like, the first property? So, well, we need to shift the cosine to t minus 3 and multiply by a step function of t minus 3. And the result, what is going to be? What we say is going to be an exponential that contains the shift. So this is going to be exponential c is 3, so negative 3s. And then we are going to have the Laplace transform of the function without the shift, which is just the cosine of 2t in this case. And that is exponential negative 3s, and then we are going to have s over s squared plus 2 squared. So this is what the first property says. If the Laplace, we know that the Laplace transform of the cosine is this function, then the Laplace transform of the shifted version of the cosine with a step is going to be the original Laplace transform, but now multiplied by an exponential. Now, what is the second property? The second property says that the cosine, we need to compute the Laplace transform of the cosine multiplied by an exponential. What is that equal to? Well, this is going to be the Laplace transform of the cosine without the exponential, which is going to be is a function of t. We know is this function of t, but now we need to, this notation means we need to shift or evaluate this function of s not at s but at s minus 5, where the 5 comes from this exponential that we have there. So we need to shift this function not into s but into s minus 5 everywhere where there is an s minus 5. So this is what we mean. So we are going to have s minus 5, and then down here s minus 5 squared plus 2 squared. So this is how this translation property looks like in an actual example. So now let's use these properties to solve a couple of examples, a couple of problems, how we can apply these properties. And here is the first example. Find the Laplace transform of the function g. Let's put it here, g of t. And g, that Laplace transform, so find the function g actually, where the Laplace transform of g is given by this expression here. Okay, so and you see the new part here is this exponential, so there is a translation property involved somewhere. So solution. How do we do this problem? Okay, we are looking for the Laplace transform of the function g. So we know that we are looking for g. The Laplace transform is the exponential of negative 3s, and then here we have 1 over s squared plus 5. Okay, so would be nice if this is in our Laplace transform table, and actually it is almost. We need to do some slight modifications so it appears in the table. You see what we know in the table is, let's put it here. We know that in the table we have the Laplace transform of the sine of at, and this is a over s squared plus a squared. That is what we have in the Laplace transform table. And the denominator looks pretty much like that. The only thing we need to do is to put a equal square root of 5. And then the denominators is the same, but we are missing the a, the square root of 5 on the top. So that is easy to fix, because the only thing we need to do is, well, let's finish writing here, minus 3s. Then we have the denominator. The denominator, as we said, is s squared plus the square root of 5 square. And now we would really like to have this number on the numerator, so we write it, square root of 5. But then we need to divide by that number, because we cannot change the problem. And now we have exactly the Laplace transform of the sine of square root of 5 inside. So we have a factor here, 1 over square root of 5. We still have the exponential, negative 3s. And now here we have the Laplace transform of the sine square root of 5 times t. Okay, but now we have one of the translation identities here. Is actually, we have that with a particular f, so we could write it like this. So let's copy that translation identity here. Where is it? It's down here. Okay. So what is this? Let's write down the translation identity we are going to use. Whenever we have an exponential negative cs multiplied by a Laplace transform of something, of f of t, this is the same as the Laplace transform of a step shifted by c and the original function shifted by c. And in this case we are going to use this. What is the shift? The shift here is 3. So the shift is given here. Okay, so the Laplace transform of the function g now is 1 square root of 5, is still there, and now that is changed into u, a step, t minus 3, and then f is the sine, so the sine of square root of 5, and now t goes into t minus 3. And of course we can put this constant inside because of the linearity of the Laplace transform, and from here we get that the function we are looking for, g of t, is nothing more than 1 over square root of 5, then the step, t minus 3, and then the sine of the square root of 5, and then t minus 3. So that's one way we can use this translation identity to find Laplace transform of functions that contain a multiplication by an exponential. One more example of this type of calculation, using now the other identity. Here we use this translation identity. What about the other translation identity? Well, it shows up in problems like this one. Find the function g of t such that now it has this Laplace transform. Okay, let's write it down a little bit nicer, like this. How do we solve this problem? Well, let's start writing the Laplace transform of g and the Laplace transform of g is s minus 2. Let me put the minus 2 over here for some reason that we're going to see in a minute. And down here we have s minus 5 squared plus 7. Okay. This looks a lot, this expression in the denominator looks a lot, and we have an s in the numerator. It looks a lot like a Laplace transform of the cosine when it's shifted by 5. What is the Laplace transform of the cosine shifted by 5? Well, that would be s minus 5 in the numerator, and in the denominator it would be s minus 5 squared plus square root of 7 squared. This is the Laplace transform of the cosine of square root of 7 times t, but is shifted to s minus 5. So very similar to what we have over there. Let me write it down a little bit nicer than over here, shifted by s minus 5. You see the Laplace transform of the cosine, and instead of s, we have s minus 5. Laplace transform of cosine of square root of 7t. And here the denominator, this is exactly what we have, but the numerator we have s minus 2, not s minus 5. And that's why I left the space, because what we're going to do is we're going to put a minus 5 and then add a 5. And then we are going to consider these terms together and these other two terms together. And we are going to split that fraction right there. So let me rewrite it a little bit nicer now. This is s minus 5 over s minus 5 squared plus the square root of 7 squared. And what is this addition here? Well, 5 minus 2 is 3. So this is 3. Okay, so we have plus, and let me put the 3 here. And then we have 1 over s minus 5 squared plus square root of 7 squared. So what we have here now is exactly the Laplace transform of the cosine shifted. And this here is the Laplace transform of the sine shifted if we multiply the numerator by square root of 7, and therefore we need to divide by square root of 7. And this is a constant that we have outside. So now that is in the Laplace, well, that we know what these two terms are. The first one is the Laplace transform of the cosine of square root of 7 times t shifted to s minus 5. And then we have 3 over square root of 7. And then we have the Laplace transform of the sine of square root of 7 times t. And all that is shifted to s minus 5. And now is when we need to use the other translation identity, which says that the Laplace transform of any function of t, for example, f could be this function or f could be this function, and then we shift this Laplace transform into s minus c. This is equal to the Laplace transform of the exponential ct, the original function that we had, f of t. So what that says, in our case, we need to use this identity twice. Once here, the other there. And then we are going to have that the Laplace transform of the function g of t is now equal to the Laplace transform of an exponential, or what is c in this case? C in this case, in both cases, is 5. So this is going to be exponential 5t cosine of the square root of 7 times t, plus we still have these factors, 3 over square root of 7, and then Laplace transform of exponential 5t sine, we are not shifting the sign here, square root of 7t. And then the linearity says that this is actually equal one big Laplace transform with this plus this. So from here we get, so let's write it down, one last step. This is the Laplace transform of the exponential phi t, and then we have the cosine square root of 7 t plus 3 square root of 7 sine of square root of 7 t. Well, if the two Laplace transforms are the same, then the functions are the same, and the function is then exponential phi t, and then we have the cosine of square root of 7 t plus 3 over square root of 7 sine of square root of 7 times t. And that is how we can use that identity to obtain the Laplace transform, the function that has this Laplace transform. Okay. So these are two examples, one to use each identity. Let's move on to our last example in this video, where we are going to solve a differential equation that has a step function on the right hand side. We assume for simplicity that we have zero initial conditions, although all these ideas still work for non-zero initial conditions. So let's solve this problem. What do we need to do? We start writing the differential equation y double prime plus y prime plus 5/4 y. This is the equation we have to work with, and here we have 3, the step shifted by pi to the right. And the first thing we need to do is compute Laplace transforms on both sides of the equation. We compute the Laplace transform. We already have the Laplace transform of the step, so what we are going to do now is use the properties of the Laplace transform here and also here. On the left side, we get that this is equal the Laplace transform of the second derivative of y plus the Laplace transform of the first derivative of y plus, now the 5/4 can go outside, and we have the Laplace transform of the function, and here the 3 goes outside, and we have the Laplace transform of the step. Okay, so now we know what this Laplace transform of the step is. We just computed. So on this side we have that this is 3, and the step, the Laplace transform of the step is exponential negative pi s over s. Okay, and on the left side we use the property of the Laplace transform derivatives into multiplications, because we don't have any non-zero initial conditions. The initial conditions are 0. This is just multiplication by s squared times the Laplace transform of y plus multiplication by s, the Laplace transform of y, plus the factor 5/4 that we had before, the Laplace transform of y. And this is an algebraic equation. For the Laplace transform of y, we can pull common factor the Laplace transform of y, so we are going to have something like s squared plus s plus 5/4, and then all that is multiplied by the Laplace transform of y, and over here we have 3, or better, let's write it like this: exponential negative pi s, and then we have 3 over s. We are kind of splitting exponential from the rest. Okay, and this looks a little bit ugly, so let's put it here. And now we divide by the polynomial that we have on the left, and that's our Laplace transform of y. The Laplace transform of y, the function we are looking for, is exponential negative pi s, and then we have this 3, we have the factor s that we have from the step function, and now we need to multiply that by s squared plus s plus 5/4. All right, that is so far the Laplace transform of the function we are looking for. So, and now what we need to do is, well, find the function such that, so find y of h. Let me write the right hand side in this way. The rational function, we are going to call it h, big H of s. And we do not include the exponential in that, only this part. And why we do that? Well, because if we do that, then the Laplace transform of the Laplace transform of y, which is what we are looking for, is going to be an exponential negative pi s, and then this function h of s, where h of s is what we said it is. H of s is that part here. Okay, so why this is useful to write the right hand side in that way? Well, because now what we need to do is we need to find a function small h of t, so that the function big H is its Laplace transform. So what I'm saying is we need to work only with the rational function, not with the exponential. Because if we find this little h such that the Laplace transform is big H, then actually we have solved the problem. Then, let's put it here, then the Laplace transform of the function we are looking for, y of t, this is the exponential minus pi s as usual, but now we know that this big H is actually the Laplace transform of little h. So this is the Laplace transform of little h of t. And now we can use a translation property right here. We can use a translation property and write this expression as the Laplace transform of a step shifted by pi, and then the function little h also shifted by pi. So in doing that, we use the translation property, and we found our solution. Our solution is y of t is this shifted step times the function little h, but shifted in the same amount. So what this property says is finding little h, so working only with this part of the right hand side is important, because if you find what is the Laplace transform of that, the inverse Laplace transform of that, you have solved your original problem with exponential. Okay? So now what we are going to do is we are going to focus only on h, big H of s, which we said is 3, and then down here we have the factor s coming from the right hand side, and then the factor s squared plus s plus 5/4 coming from the left side. And notice that this function h is what we said, does not include the exponential, does not include the exponential, and well, also of course is not sorry, is not in our Laplace transform table. Okay, but then what do we do to try to find little h? Recall now, the only thing we are doing is trying to find little h such that the Laplace transform is this. Well, we do partial fractions. When we have something that is not in the Laplace transform table and is a product here of two polynomials in the denominator, we use partial fractions. So let's write that down. We are going to use partial fractions. But the particular form of the partial fraction depends on whether this factor has roots real or complex. If it has real roots, then we should write it as s times s minus one root and s minus the other root, isn't it? And then we do partial fraction with 3 factors. Or if it has complex roots, then we keep it as it is. So which case it is? To figure it out, we compute the solutions. So we compute the roots, that is the solutions of s squared plus s plus 5/4 equals 0. We have a formula for that, which is s plus minus is equal 1/2. Then the factor is 1, so negative 1 plus minus the square root of 1 squared minus 4 times 5/4. Okay, that's simple. So what are we going to have? S plus minus, we are going to get 1/2, then we get negative 1, and then plus minus the square root of what do we have here? 1 minus 5, so negative 4. Well, this is going to give us complex roots, isn't it? Actually, this is actually equal to negative 1/2, and then plus minus 2 over 2 is 1, so I. So we have complex roots. It's not important exactly what are the roots. The important thing is they are complex. So in those cases, when we have complex roots, what we do is we complete the square. We complete the square in this factor, but we are going to do it later. We don't need it now for the partial fractions, and we do it later. Right now we know that we need to keep this factor all together, so the partial fraction decomposition now in this case is going to be that h of s, which is here, h of s, which we said is 3 divided by all that, s squared plus s plus 5/4. This is going to be one number divided by s, plus now we have a polynomial in the denominator. We have a polynomial degree 2, s squared plus s plus 5/4. Okay, so in the numerator we need a polynomial 1 degree less, so b s plus c. So this is the correct partial fraction decomposition. Now let me emphasize that by making a little highlight here. So it's left as an exercise. I'm gonna put the calculation at the end of the video, but exercise show that we can compute A, B, and C, and A is actually 12/5. B is equal C, and they are both equal negative 12/5. So it's an exercise for you to do it. I'm going to show the calculations at the end of the video. The important thing is A, B, and C are well-known numbers after we compute them. So from now on, I'm going to keep calling them A, B, and C, but recall A has this value and B and C have that value. So since A, B, and C are well-known numbers, the Laplace transform of the function we are looking for, the Laplace transform of y, now looks like, recall we still have the exponential minus pi s, and now we are going to have parentheses and a over s plus, we have b times s plus c, and down here we have the whole polynomial s squared plus s plus 5/4. All right. But what do we do now? Well, this factor, we know what to do, because we know that the Laplace transform of 1 is exactly 1 over s. So what we have here is the Laplace transform of 1 multiplied by a. And what do we do on the other factor here? We complete the square here. So let's write down what we have so far. What we have is exponential minus pi s, and now here we have a Laplace transform of the function 1, and here everything is the same, so we haven't worked yet. So let's keep it as b times s plus c, and down here s squared plus s plus 5/4. Okay, now let's focus on the second term. And on the second term is where we need to compute the completion of the square. So complete squares. So what is that? So complete the square means grab the denominator s squared plus s plus 5/4 and write it down as s minus some number a square, this is the complete square, plus the rest, and the rest should be some number that we can write it down also as a square. So that is a complete square. How do we achieve that? Well, recall we start with the original polynomial, which here it is. The first term, we leave it as it is. Now, in the second term, recall we have an s here. We multiply by 2, and then we divide by 2. And recall s means that we are multiplying by 1, so this is the original one that we had. So we have a factor 2 times 1/2. And now what we do is, okay, so we are going to grab this 1/2, and we are going to add it square, and then we are going to subtract it square, and we still have the original 5/4. And now the first 3 terms, we're gonna put them together. Why we are going to put them together? Because this is the complete square. And why this is a complete square, this thing here? Well, because we have let's go to a different color. Recall that whenever we have, where do we can write it down? So suppose we have alpha plus beta square. Well, this is alpha square plus 2 alpha beta plus beta square. And use this relation with alpha equal s and beta equal 1/2. And then you're gonna see that, oops, what we have here is that. Therefore, for these two values, therefore we can write it down in that way. So we end up here with s plus 1/2 all square. And then we have 5/4 minus 1/4. So minus 1/4 plus 5/4. Well, that is simply 1. So we end up with s plus 1/2 square plus 1. All right. So this is the complete square in our case. We can write the denominator in this funny way. So let's go back here and let's put that in there. So what do we end up with? The Laplace transform of y is, then we have the exponential minus pi s, and then we have a factor with the Laplace transform of 1 plus, and now we have b that multiplies s. I'm gonna put this c over here. Far away is nothing to worry about. And here we have s plus 1/2 all square plus 1. And notice that what we have here is the denominator of the Laplace transform of the cosine shifted by 1/2 to the left. So we need to, if we have plus 1/2, we need to put it here. So this is that's why I left the space, because b is gonna multiply now all this. Plus 1/2 minus 1/2. I want the same shift I have in the denominator, I want it in the numerator. So I'm gonna consider these two terms as one term. I'm gonna put parentheses, and I'm going to multiply b by that and b by this, the other term. I still need to close the last parenthesis. And then we are gonna have exponential minus pi s that multiplies this whole thing. A Laplace transform of 1. And then what do we have? We are going to have b that multiplies s plus 1/2 only. And then we are going to have plus c minus b over 2. You see where the minus b over 2 comes from here. Here is the negative sign. And everything is divided by s squared, s plus 1/2 square plus 1. And now this fraction, I'm going to split it exactly here. Split. And we end up with this very nice formula, which is the Laplace transform of y is equal to the exponential minus pi s, as always, is still there. Then we have a Laplace transform of 1 is always there. And now we have two terms, because I split that fraction into b, and then we have s plus 1/2 over s plus 1/2 square plus 1. And then we have plus the other term, which is c minus b over 2. Recall, these are numbers that we can compute, a, b, and c, and any combination of these numbers. And then we have 1 over s plus 1/2 square plus 1. Let's put a big parenthesis here with that one. Okay, but now we use our Laplace transform table, and we realize that in that table we have that the Laplace transform of exponential at cosine bt is exactly what we have here, is s minus a, and down here is s minus a square plus b square. So if we choose a to be negative 1/2 and b to be 1, well, that is what we have here. And in the Laplace transform table we also have the Laplace transform of exponential exponential at sine of bt. And this is b over s minus a square plus b square. And again, with the same a and b, we get that. So our function, actually, the solution of the problem we are looking for, of this problem, y of t, is exponential minus pi s, and then what do we have? We have a multiplying the Laplace transform of 1, then we have plus b, and this is a Laplace transform now, a Laplace transform of exponential b is 1 and a is negative 2, negative 1/2, so negative t over 2 cosine of t plus this constant c minus b over 2. Looks complicated, but it's super simple. It's just a number. The Laplace transform of exponential minus t over 2 sine of t. And there it is. We almost there. This is the same as exponential minus pi s. And now we have one big Laplace transform of a plus exponential minus t over 2. I'm going to put one Laplace transform for this function times that, this function times that. I can pull common factor the exponentials. And then we are going to have b cosine of t plus c minus b over 2 sine of t. And here we are. This function here is nothing more than little h that we mentioned before. We found our function little h. So the solution we are looking for is Laplace transform of y equal exponential minus pi s Laplace transform of this little h. So we know what is going to happen. Now we have the translation identity that says that this is going to be equal the Laplace transform of the step t minus pi h t minus pi. Again, this is the translation property. So this is our function, our solution. Our solution finally is y of t. What we said is going to be a shifted version with a step of the function little h shifted by pi. And now if we write it down explicitly, the solution that we obtain is the step t minus pi. And then what do we have? Well, big parentheses, and we have a. We cannot shift the constant, so it's a. Then we have plus b. And now, well, actually, let's pull the exponential common factor. So we have exponential, and now we need to shift t into, we have the negative sign. Now we shift t minus pi, and we still have divided by 2. And then here we have b that multiplies the cosine, and now we need to shift it, t minus pi, plus this other constant, which is c minus b over 2, and then sine shifted t minus pi. And we close that bracket there, and this here is our solution. Something like this. And recall, let's put it here, recall that we know a and b and c. Well, we haven't computed, but this is 12/5, and b is equal c equal negative 12/5. So that is our solution. And down here, somewhere here, I have the calculation. I'm going to move it a little bit higher up. Somewhere, this is the calculation to obtain what these constants are, how we obtain those constants. That was the exercise. So you can try to do it yourself and then compare with this calculation. So this is how we use the translation properties and everything we know to find solutions of a differential equation with a step function on the right hand side. This is a good place to stop. See you guys in the next video.